All right, this is the second half of the notes concerning isotopes, which involves radioactivity. Because remember, we talked about isotopes are a lot of the isotopes that are isotopes of the elements on the periodic table are actually radioactive. So going along with that, then we need to discuss what is radioactivity. Well, in order to understand radioactivity, you have to understand that these elements that are radioactive, what they do is ultimately they change over time. Wait a minute. We go back to Dalton's atomic theory, and we said atoms can't change to different elements. Here's one of those issues that it's not what I want to say like common for elements that surround us. Excuse me, there are those elements that are radioactive that do actually break down over time, and it's a long time, but they do break down and they do change into other elements. And that's what we're going to look at real quick today, is how radioactivity occurs and what it is. So to start with, to get an understanding of how this breakdown works, it's called half-lives. Right? And there's a little paragraph at the beginning of the notes where it says, look at a graph of coin flipping activity. On that, what I'm going to do is we're not going to actually do the activity unless you'd love to, but it takes a while to do. But if we flip a coin, so we're going to make a real quick graph here, and we go. This is trial number one. If I flip the coin 100 times, okay, so I just take a coin and flip it 100 times, how many times would you expect to get heads? Well, you'd probably expect it to be about 50. So let's go up on this side and we'll put our scale. All right, so that takes us all the way up to 100. So now if I were to put my points on here, let's see, we'll go blue. So at 0, before I start, I'm going to have 100 times. All right. Then my first trial, what I end up with is I end up with 50. So I'm going to get 50 heads. Now, after I've done that, I got 50. Now what I want you to do is I want you to take how many times you got heads and flip the coin that many times. So if we got it 50 times, then now we're going to flip the coin 50 times. Right? If you flip the coin 50 times, then how many times do you expect to get heads? Well, if it's 50 times, then you probably expect it to be 25. So we're going to put it dot at 25. Now we're going to take that coin, we're going to flip it 25 times. So how many times would you expect to get heads? Well, half of 25, that's what, 12 and a half. So let's call it 12 or 13. So that's going to be about here. Right. Then we get our fourth time. And that means, okay, let's flip, let's say we had it 12 times. So we flip the coin 12 times. How many times would you expect heads? 6. So we put it down at 6. That's about here. Notice already, if we like connect the dots, is it making a straight line? No, it's not making a straight line. Okay. So now we got 6 times. So we flipped that coin 6 times. We would expect to get it for the fifth one 3 times. Then we flip it 3 times, and we would expect to get like 1.5, so right in here, right? Now, in theory, right, should you ever actually get to 0? Well, actually, really, no, right? I know in the case of the flipping coins, you would finally get to that point where you might flip it once and don't get heads and it's all over. But what these things are is these things are actually called half-lives. And if I connect these dots, then this is the graph that we end up with, right? And what it is that this is 1 half-life, this is 2 half-lives, this is 3, this is 4, this is 5, this is 6. And it's how much of that radioactive material is left, given that we started with 100 pieces of it. Now, if it takes it 5,000 years for half of it to break down, right? So kind of like thinking, if it takes you 5,000 years in order to flip that coin 100 times, right? Then this span from right here to here is 5,000 years. So if we had that much of the radioactive material left, then this object would be 5,000 years old. If we had this much left, we have 25 out of the original 100, then this is another 5,000 years. So now we would say that that object is 10,000 years old. And if we had this, if we had, what was that, 12 of the original 100 left, and we'd have 3 half-lives, which is 5,000, 5,000, 5,000. So we're at 15,000 years, right? So it's all about these half-lives, and that's how we can determine how old something is. And the substance that does that is carbon-14. That's the one that we use for a lot of our fossil dating because it has a half-life of around 5,000. We can use other elements like uranium. We can use that, but that has a half-life of around 2 million years. So we can use that to determine the age of the Earth. So all these radioactive isotopes do have half-lives that have been determined. They've been calculated. How would you find out what they are? You can just look them up. Just do a search for isotope half-lives, and you get a list of all the isotopes of all the elements, and it'll tell you what their half-lives are. All right, so calculating half-life, number one there says radioactive elements decompose to different elements over time, and that is a very specific amount of times. That's what the half-life is. Now, as they decompose, letter B, they release energy, and they release energy in 3 different possible ways. And the first one is called a beta particle. And what a beta particle is it is a negatively charged particle. So that negatively charged particle, if you remember from the atom, it's an electron. Now you might go, oh, okay, so it loses one of its electrons, makes itself into an ion. But that's not what ends up happening, right? What actually happens is you get a neutron from the nucleus. It actually turns into a proton and an electron. Oh no, that's kind of weird, isn't it? To know that a neutron is made up of a proton and an electron, which, now when you really think about it, proton's positive, electron's negative. So you put the two of those together and they would neutralize each other. That then is a neutron. Right? So it breaks down and the electron goes floating away as a beta particle. And we end up with a proton left. So if we end up with a proton left, what just happened to the number of protons in the nucleus? Well, it just went up by 1. So if we were to look at this and get rid of my graph here. So if we had carbon-14 and we were looking at protons, neutrons, and electrons, right? And really in regards to these isotopes, we really don't have to worry about electrons. So this is carbon, so he has an atomic number 6. So he's got 6 protons. And then 14 minus 6, he has 8 neutrons. So in the case of this carbon-14, he's going to take one of these neutrons and turn it into a proton and electron. The electron is going to go floating away as a beta particle. Well, now all of a sudden we end up with an extra proton. So now instead of having 6, I have 7. Well, if I have 7, is that still carbon? No, because carbon's got to have 6. So what is this element? Well, it happens to be nitrogen is element number 7. Well, let's figure out what its mass is. Well, he just lost a neutron, so he now has 7 neutrons. Remember that mass is protons and neutrons added together. So the mass of this thing is 14. Well, that's kind of weird. So that carbon-14, when it turns into nitrogen-14, doesn't lose any mass. But remember, at the beginning of this chapter, we said that electrons have no mass. And that's what it lost, was what would be equivalent to an electron. And electrons have no mass. It maintained a proton. So we end up all of a sudden taking a carbon-14, it turns into a nitrogen-14. And later on in these notes, we'll find out that this nitrogen-14 is stable. It's a stable type of form of nitrogen. So we just took this radioactive compound and turned it into something that was not radioactive. Now, it takes about 5,000 years for this to happen, for half of the carbon-14 that's present to turn into this. So if we started with 100, let's say 100 pounds of carbon-14, then it would take 5,000 years, and then we'd have 50 pounds of carbon-14. And that other 50 pounds would have turned into nitrogen. And then we go another 5,000 years, like the flipping the coin, you get half of 50 is 25. So now we're at 10,000 years, and now we have 25 pounds of carbon-14 out of the original 100, and 75 pounds have turned into nitrogen. Okay? So that's what the beta particle is. Now we go to the second one. Second one is a gamma ray. And gamma rays, they have no charge. They're not a neutron. It's just energy. And if you remember when we, in the other notes, we talked about light, we had the electromagnetic spectrum. Well, gamma rays are way over here, right? And they're really, really damaging. They are destructive to human tissue. So that's a really not a great thing that's given off. So you definitely don't want to be around radioactive material. Then we have the third one, and the third one is interesting also as how it works. It's called an alpha particle. What an alpha particle is it's a loss of a helium nucleus. I know that seems weird because we're going to lose a helium nucleus out of another atom. And the one I want to show you is we're going to do the same idea. We're going to use uranium-238. So we have uranium-238. His atomic number is 92. So because it's 92, we're going to go, he's got 92 protons. And if we subtract these two, gives me, 146 neutrons. So now if I subtract, I'll use a different color, we're going to subtract a helium nucleus. Well, a helium nucleus is 2 protons and 2 neutrons. So we're going to subtract that from this. So when I do that, we end up with 90 and 144. So now if it's got an atomic number of 90, then it's no longer uranium. So we have to go to the periodic table and go, well, what's number 90? Well, that's thorium. So now we're talking, this is thorium, and his mass is 234. Okay, so this is number 90. Now this takes 2 million years for this to occur, for half of this uranium to turn into that. Now if it does it again, take another 2 million years, right? It does it again, so we're going to subtract 2 protons, we're going to subtract 2 neutrons, and goes through this, we end up with number 88 and 142. So according to the periodic table again, we look at that and go, what's number 88? Well, that's radium. So we go Ra, and that's 230, and that's number 88. So that's another 2 million years-ish, right? Now we'll go through another 2 million years, and we're going to subtract another helium. So we do that, we get number 86 and 140, and that's radon. Oops. I did the wrong letters. I'm sorry, not radon. Radon, there we go. And that is 226 and number 86. Okay. So now this is like 6 million years for this to occur to make radon. Now, where in the world does radon come into your life? Well, and I put it inside your notes, it has in parentheses, says basement test. And it is that one of the things that some people or people test for, especially when they buy a house, they test for radon in a basement. And what it is that it comes from the breakdown of uranium over like 6 million years way underneath the ground, and it becomes a gas. And that radon, because the gas slowly moves up through the earth, and if it happens to come up right where your basement is, it'll fill your basement with radon. A really, 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 really small amount. You're not going to smell it, not going to see it or anything like that. But what you will know ultimately is because this is radioactive, it can make you have cancer or other side effects later on in life. So it's unfortunate. So people have radon tests done, and if radon is present, then what they'll do is they'll actually come in, they basically seal the basement, like paint it, and then they'll put a pump down underneath the basement floor, and they pump out the gases and send them outside so that the radon doesn't end up inside of your basement. All right, so how do we decide if these elements are stable or not? Well, what we do is we look at the ratio of neutrons to protons. And looking at my time, I'm going to go to video number 3 so I don't run out of time. We'll talk about that real quick. So see you in number 3.